Computers. We all use them every day for almost everything. Inside the computer there are binary machines that control everything about the system. Wait, but what is binary? What exactly does that mean? And how does this simple computer circuit is related to math? So let's find out in the following video. You can imagine binary as a light bulb. When it's not on, is called 0 or logic low. When it's on, it's called 1 or logic high. And 0 and 1 are all the numbers in binary. So in decimal there are 10 numbers, and in binary there are only 2. So let's look at this form. 1 is 0 is 0, 1 is still 1, and 2 becomes 1 0, and 3 is 1 1, 4 is 1 0 0, and so on. Which is very similar to decimal, because 9, the next one is 1 0, because we ran out of digits. And we can also do computations on binary numbers like how we do in decimal. These are called logic gates. This symbol represents the AND gate. This symbol represents the OR gate. This symbol represents the NOT gate. This symbol represents the buffer gate. This symbol represents the NOT AND gate or the NAND gate. This symbol represents the NOT OR gate or the NOR gate. This symbol represents the exclusive OR gate or the XOR gate, and this is the exclusive NOT OR gate or the XNOR gate. Let's look at them one by one. The AND gate, as you may have guessed by its name, is the AND. So the output will only be 1 when both of the inputs is 1. The table at the right is called a truth table and it represents the 1 and 0s in each case. Similarly, the OR gate functions like the AND gate, but as its name suggests, it is OR. So the output will be 1 with 1 of the input is 1. And then the NOT gate. As you might have noticed, there's only one input, so the NOT gate only refers to 0 and 1. And 1 becomes 0 and 0 becomes 1. Next is the buffer gate, which does absolutely nothing except for buffering. Next is the NOT gate and AND gate put together. AND gate and a little dot. This is the NOT AND gate or the NAND gate. As you can see, it actually functions very similar to the AND gate, but at the output side, the 0 and 1 are flipped. 1 should be 0 become 1, and 1 should be 1 becomes 0. And the NOT function can also be done to the OR gate to create the NOT OR gate or the NOR gate. Also, the 0 and 1 are flipped, and 1 should be 0 becomes 1, and 1 becomes 0. And here's where it gets a little bit complicated. Exclusive OR gate. It is similar to the OR gate, but when both of the input is 1, the output is not 1, but is 0. So there's 2 0 and 2 1s on the output side. And the NOT function can also be done to the exclusive OR gate or the XOR gate to create the XNOR gate. It does the same thing as the exclusive OR gate, but at the output side the 0 and 1 are flipped. As you might have noticed, these are quite really simple computations. So when we need more complicated, we need to come up maps. So, for example, this is the common notation of the Karnaugh map. The AND is usually not noted, the OR is represented by the plus sign, and the NOT is represented by the apostrophe or the prime or whatever you call it. And 1 is called 1 and 0 is not 1 in the context of Karnaugh maps. You can't say that 0 is 0 and 1 is not 0 because that's the convention. For example, look at this truth table. There are 3 inputs, the A, B and C, and the output will be 1 if the input is 0 0 0 or 0 1 0. For all other cases, the output will be 0. And we need more logic gates to create this function. Let's draw it in the Karnaugh map. It looks like this. In the vertical side there's 0 and 1, and the horizontal side there's the B and C, 0, 0, 0, 1, 1, 1 and 1, 0. Because the output of 0, 0, 0 and 0, 1, 0 is 1, so they're written 1 and highlighted. We can observe that in both highlighted cells, the A is both 0 and the C is both 0. We remember that 0 is represented by the NOT, and two different notes and will be added by the AND gate. So the answer is not A and not C. So that drift table is not A and not C. For example, if we have something more complicated like this, 0, 0, 1, 0, 1, 0, 1, 0, 0, 1, and all others are 0. Now, if we try to draw it on the Karnaugh map, we might experience a bit problems, because there's actually two or more groups colliding together on the Karnaugh map. As you can see, if we try to make 1, 0, 0 included, then actually in this graph 0, 0, 0 will be both green and blue, but due to technical reasons I can't draw it together. But the 0, 0, 0 is collided, so if there are two or more groups, two or more colors, we have to use an OR gate between them, and the vertical one, the blue one, and the BC is 0. So the answer to that is not A and not C, or not B and not C. That's all for the introduction of binary, Karnaugh maps and logic gates of today. And I hope that you've understand the logic gates and the Karnaugh map expression throughout this video. This is actually my first math video including manim, and it is actually a submission to the SOME2 Summer of Math Composition competition, and it was made in quite a short time, so I hope that even if you didn't like the video or you didn't understand much details of the video, I can hope that you can appreciate my work and please like and subscribe if you have liked it. Thank you.